here's the story. It's exactly what I just told you. You've got a population, the population of middle schoolers that they took this intervention for. They calculate their sample mean. The sample mean is not the population mean, it's an approximation of the population mean. How good that estimate is depends on the behavior of those y1s through yn's and the effect that has on that sum. That sum you've seen before. You just did that in the last homework where you're looking at sums of random variables. That's a function. So you're actually transforming or doing a change of variables from your original variables and you're looking at that sum. And so that's why they made a big deal and you have all those problems to do on it. A statistic is a function of the observable random variable in a sample and known constants. When I had Marina in 376, the very first day I asked the class what the sample mean is. It's actually a function. It's a random variable in its own right. You change the sample, you make the sample bigger. We actually did a little experiment. I wrote some code and you can actually see if I keep flipping a coin, that sample mean starts changing and that sample mean has its own distribution. And so in 376 you did experiments like this actually, where you're looking at taking means, and bootstrapping was one of the things you did, where you were drawing in a bucket and keeping, you're really actually calculating the mean over and over, and it has its own sample distribution. So those are functions. So that these are two things, the sample mean, the sample variance. You can think of a whole bunch of other stuff that you got from 376 where you had similar things. I loved 376. That was a good class. It was not my wheelhouse, but I really loved teaching it. All statistics are functions of random variables observed in the sample. All statistics are random variables. I remember I said this in our class, and the rest of the class went, what is she talking about? But the mean is a function. The sample mean is a function. The statistics themselves, the sample mean has its own little baby probability distribution. And they are called, this is called the sampling distribution. So I think we used this language, sampling distributions, when we did bootstrapping in 376. I'm pretty sure we did. Kuiper, how many of you guys took 376? Sound familiar? We talked about sampling distributions, and did you guys have to do our code like this? Bootstrapping? You didn't have to do bootstrapping? Yeah. Bootstrapping is exactly that, right? So I gave you one example, regression to the mean. The other one I did, I probably have it somewhere. So I'll pull it after this because it's going to actually mess up my recording. But I had wrote some code where I can simulate a coin flip, and you can actually see those means changing. All right. Again, these are tips for you because I'm task-oriented and I'm thinking about the WPR. So I would review theorem 7.1, 2, and 3 and put them into the Brown bombers so that you have them if you need to. So there were a couple problems on the last homework where you really had to go into the theorem and pull what you needed and you could solve the problem. So that's what you need in your Brown bombers, in a way that if you get asked a problem along those lines, you can go whip over and go to your Brown bomber, pull the information you need, and address that. On page 359, what's really cool is they derive the student T distribution with n-1 degrees of freedom. And if you, in 376, you really learn about the T distribution in a way I think you didn't learn in 206. I didn't teach 206 yet, but I think that in 206 you probably look at things as formulas and tables. In 376, you're actually looking at the degrees of freedom and why this is not the normal distribution, why I actually have to use this T distribution. So you're looking at more nuanced things about the T distribution, and here they derive it, and they show you where they come up. It's an approximation, actually. So there's an example of a type of problem. It's example 7.6, and I'm going to go through that example to show you, because this is the problem that Colonel Watts and Colonel Clark keep talking about, so I want to actually go through it a little bit so that you can see what it is. So you have in this problem, you have a wire. You're looking at the tensile strength of the wire, and you know that tensile strength is normally distributed with a mean of mu and a variance of sigma squared. So those things are not given to you. Just like the problems in 376, I think we did the shooting problem. We don't know the means. Remember where we shot the Navy boat? So we don't know the answer. We're getting it from the sample itself. We're estimating it. So those things are not known. You take that wire and you chop it into 6 pieces, and you have 6 different pieces from that roll. So you now have a sample, and Y sub I represents the tensile strength of the piece piece number I. So I labeled the pieces up there so you can see them. So the population mean, just like we did in 376, we don't know it, but we estimate it by looking at the sample mean and the sample standard deviation. So I think in the Kuiper book they used little m's and little s's for what this is representing, that you're working with a sample. So the question here is to find the approximate probability that the sample mean will be within 2 standard deviations of the true population mean. And you don't really have the standard deviation, so you're using the sample standard deviation. These were the kind of problems we calculated in 376 all the time. Right? Do you kind of remember that? So the first step is to set up your probability function. So you want the probability, so you're looking at the error. So let me see if I actually have. So Y hat, or Y with the bar over it, is your sample mean. Mu is the unknown population mean. You don't know what it is, but you want to calculate the probability that that error between the two is between 2 standard deviations away, the sample standard deviation. So you should recall these kind of formulas from 376, because we did that. Everybody like 370? I love 376. I thought it was a fun class. So then the second thing is to reformulate that so that it's between numbers, because this is a calculation, so you actually look up stuff. And so you reformulate that problem so that you have a number in the center. And it turns out that that expression in the center is this is the T distribution. If you look at page 360, I recommend putting that T distribution formula in your Brown Bomber. You already know it because we've done it in 376, but just, you know, if you're like me and you forget where you put your keys, then forget where you put your cat card. Anybody? Okay. So, you know, just put it in a notebook so you have it ready to go. And if you're actually really organized and put little like tabs in your notebook, then you can actually find things quickly. Like this is about standard distributions or well-known distributions, so that you can have it. And then the book, have it open to the back flap so that you can pull things from there quickly. So you need to recognize that the thing in the center is the T distribution. Go to the back of the book. Degrees of freedom. Degrees of freedom, if you recall, we did this also in 376. We have, in our case, we have 6 pieces of wire. So 6 minus 1 is 5. It's 5 degrees of freedom. And so you go in the back of the book, under 5 degrees of freedom, you have, I think it's called Appendix 3, Table 5. It's almost the first thing I flipped to when I opened the book. And you're looking at the right tail. So this should also be reminiscent of 376. You're looking at a right tail. To the right of 2 on degrees of freedom 5 is 0.05. So that's your beta value. So they have 0.90 in the book, but I think it's 0.95. I'll ask Colonel Watts to confirm. So they did this, and I think we did a little bit of this in 376. We compared this to a normal distribution and said, what if we just assume this is a normal distribution? Because you remember, with the degrees of freedom going higher and higher, eventually you get enough degrees of freedom that you're close enough to the normal distribution so you can make some assumptions. And so they actually have it in your book. They calculated as if it was a normal distribution, and it's pretty close, around 0.95. Okay, good? So again, with that little remainder time you have after you make sure you got to ask me questions. If you go back to your revisions and you were just checking the box, I don't care. Come back and say, ma'am, I was just checking the box. Tell me what I really got wrong and how I can understand this. Because if the problem changes slightly, you should be able to understand how to change what you're doing. So remind me at the end of like this to show you something that I have for you that you can put in your Brown Bomber that will help on one of the problems. All right, last but not least, this is so cool. It's a central limit theorem, and it's why we talk about normal distributions so much. The central limit theorem, Colonel Kaminsky was telling me that in education, stat education, they're trying to go away from normal distributions and just teach distributions in general, like we do in 376, but at a 206 level. But the reason that they do normal distributions is that things generally are a normal distribution. So there's a beautiful picture I can show you with the individual weights where they actually look like that. They're normal distributions. And if you have more and more data, and if you start looking at the sample means, like for example with the coin flipping, you start looking at just the sample means, they start to form a normal distribution. With the bootstrapping also, when you start piling more and more bootstrapping simulations, you start to see it formulating on R and it'll look like a normal distribution. So they're important. So here's how it works. I've got y1 through yn independent and identically distributed variables with mean and standard deviation known. And by the way, I just realized that maybe when you have this strictly less than infinity, you might have not seen that before. What it means is that sigma squared is not infinity. It's a finite number. That's what that means. So if you define un to be the function that I have up there, which reduces down to this y bar minus mu divided by the standard deviation, the way you can think of that number is you can think of that number as the error of the sample mean relative to the population mean that's normalized by standard deviation. So that's how I think of it. Again, I do a little bit more machine learning, so I think about things as normalizing. So you're taking the variation, you're normalizing by that variation, and you're looking at the error between your sample mean and your regular mean. So that's what that number looks like, where y bar is, of course, your sample mean. Then the limit of those sample means is exactly the normal distribution. So if I have enough data samples, like if I have enough growth of those samples, then I can assume some things about being normally distributed. That's what it tells you. So Colonel Watts will always tell me, like if I'm trying to do something, it's just like, well, you know, we might not have our assumptions satisfied, but we can say something that we might be close to having them satisfied. She's using the central limit theorem. So there's two examples in the book. There's 7.8 and 7.9. I would pull some trigger words out of those samples, those two examples, so to key you in that you are going to have to apply the central limit theorem. And they're very standard. It's almost like when you get a bunch of problems on it. I'm imagining you sitting on a test, you get a bunch of problems, and you're going to look at them, they're all going to look different. So you need to somehow let yourself know quickly what's the key word here that's going to match me to what I have in the brown bomber. All right, that was 4 sections. I'm skipping over the examples because you can look at them in the book. I kind of looked at the examples that they had in there and thought, yeah, you guys will read it if you have time. I really recommend putting something down in your book. So let me show you one more thing.